General Physics 1. And now, here's your professor, Varanga Pereira.
Hello everyone, welcome back. We'll continue the topic of kinematics today, and we're going to get into some more complex problems. We have now talked about how to deal with one-dimensional motion, and we'll get into multiple dimensions as we get along. So one of the websites that's really handy is PHET, and if you search for Colorado, the University of Colorado, the first link that shows up is the PhET simulations, and if you click on physics, and if you're taking other subjects, there are other topics as well. So there's a lot of simulations that you can play with. If you can get your hands on some object to visualize, then that's good. But sometimes you can't do that and you don't have access to a lab maybe. The simulations are pretty good to visualize what's going on. So when it comes to projectile motion, there's one on projectile motion is here's a cannon, and then you can change the direction and shoot off an object, and you can see how the object moves across. You're now moving in the x direction and the y direction. No longer is this just a one-dimensional motion, it's now two-dimensional motion. So this is what we want to try to understand, how to model this behavior, because it doesn't just apply to cannons and golf balls, but if you're playing tennis. There's lots of other applications where maybe you want to send off an object, it travels in two dimensions and ends up somewhere else, and you want to know how long it takes and how fast it'll get there, that sort of thing. We're going to talk a lot about vectors today, and it's math heavy because we need to set ourselves up for two-dimensional motion, that is projectile motion. If you're talking about a golf ball, you're talking about the trajectory of a tennis ball, basketball, any kind of object that's moving in projectile fashion, it requires some additional math. So we'll need to talk about trigonometry, and we'll build up from there. We'll talk about vectors. Particularly unit vectors are going to be something that's critical. Once we have that, we can talk about projectile motion. We can talk about how far up does it go, how long does it take for something to go and come to the ground, things like that. Let's take a look at this question. I'm going to zoom in here. You should see the answer choices on your device. Let's pause for a minute and a half. Take a shot, really work this out for yourself. The more you try this out yourself, the better you're going to learn. So take a shot. If you answer a certain way, we will go through the answer at the end of this, so you'll know what the correct answer is. You're welcome to change your answer. We want you to understand how to do this, so you don't feel like you shouldn't try because you don't want to get the answer incorrect. It's fine. We will all get to the correct answer. All right, so let's pause for a minute and a half and then we'll come back. Let's take a peek at what are we thinking so far. 6 seconds, popular answer. Getting a few others here as well. Let's see how you might set this up. Rough sketch of what they're talking about. I haven't put in some of the detail. This is just from last time. There's a hammer that is a certain distance away from the surface of the moon. We're picking our reference point, the surface of the moon, to be position 0, and we're measuring distances up being positive. As I said before, that's up to you. You could have put the position 0 at the point of the hammer. You could measure downward to be positive. As long as you're consistent, you're welcome to do that. This just makes more sense to me. The other thing that we want to add to this is to give you a little bit more detail here than the previous problem. We are modifying the previous problem a little bit, and that is that what happens if he threw it up at 10 meters per second. That's the additional piece of information that we have here, unlike just dropping it straight down. The hammer goes up, grab an object. If you haven't done this already, grab a paper clip, throw it in the air. You can model what this would do yourself. This hammer would go up and momentarily come to a stop and then start falling back to the ground. So the hammer would go up and stop. And that is what we want to do, is picture this in reality. What would it look like if you actually did this yourself? We know that the hammer would travel, momentarily stop at the highest point. So if I were to draw the velocity, 10 meters per second, in terms of these arrows, what could I do? Let's do it on the side. Maybe I represent 10 meters per second like that. And we know as the hammer goes up, it seems to be getting slower and slower. So I can use these arrows to indicate velocity. So this long arrow could be 10 meters per second and smaller till it gets to 0. And we know that it'll slowly at first and then get faster and faster and come back down. So you can see just in an abstract way, I'm representing what the hammer would do. And what I'm showing here is the velocity of the hammer. At the highest point, you'd get that the velocity is 0 meters per second. That's the key to doing this problem, is knowing that the highest point and the velocity are related to each other. At the very highest point, the hammer, the velocity will momentarily be 0. That's key. Now, once we identify that, so we've reasoned our way through this problem, we've drawn a sketch, we've said, okay, what we expect this to do, and to come up with all this. Notice no equations so far. I haven't thrown numbers into an equation yet. I am trying to reason. This is very critical that you spend a lot of time initially at this stage of the problem to say, okay, what's going on? Do I really understand what's happening here? So now you understand the key point, you can go ahead and do this problem. We talked about 4 kinematic equations last time. So we want to determine which one we should use. So let me pull up our 4 here. So we have that. We have an equation that relates position and velocity and time. We have one that relates velocity, acceleration, and time, position, velocity, and acceleration, velocity, acceleration, and position. These are the 4. Now, as I said before, how do you know which one to use? Let's think about what first are we trying to solve for. We're trying to solve for how long is time, how long would it take for it to reach the highest point. We're solving for time. So using this equation is not going to get us what we need, because this equation doesn't even have time. So it's not to your benefit to use this equation in this particular problem. This could work, maybe this could work. At least it has time in it. The other thing you want to do is think about, okay, what do I know about what's going on? For one thing, we've reasoned our way to the fact that the velocity at the highest point is 0, so we know some information about the velocity final, because if we're considering this the initial, 10 meters per second, then this is the final. So we know something about the before and after for the velocity. And we know the acceleration. We calculated that last time. We found what the acceleration of the moon is, the acceleration due to gravity of the moon. We calculated that. So of the equations, this looks very promising because, look, it's relatively short for one thing instead of this one. You have the initial velocity, you know the final velocity, acceleration is known, and that way you can solve for time. That's how you think about when you have the 4 kinematic equations. It's just thinking through them. So you want to look at the 4. First, what are you trying to solve for? Are you trying to solve for time? Okay, then that doesn't work. Then after that, it's a matter of what do I know? Do I have enough information about the initial velocity or the initial position to solve this? And sometimes you can use 2 equations to give you the same result. So in that case, pick one, whatever is your favorite. In this case, what I'm going to say is the final velocity is equal to the initial velocity plus at. I'm trying to solve for time, so let me isolate that first. I'll say time is equal to final velocity minus the initial velocity divided by the acceleration. If you isolate your time, you should get that. It's only when you get an equation for the variable you're trying to solve for should you be putting in numbers. So at this point, you can say, okay, the time is equal to what is the final velocity, 0 meters per second. The initial velocity was 10 meters per second. And also be careful with the acceleration. So we want to put a negative 1.63 meters per second squared. Negative because of our sign convention. The acceleration is downward, therefore negative. And so you have to be careful about the signs. So if you put all this, 6 seconds or so you should get 6 seconds, the time it takes for the hammer to reach the highest point. You can see that these kinematic equations are actually very powerful because David Scott on Apollo 15 didn't throw the hammer upward, but you can do these hypotheticals, and if you're an astronaut in the future, you go to the moon and you do this experiment yourself, you should get this. This number you can measure, and then it will be 6 seconds. It's a powerful thing. You can do hypotheticals. Questions, Jericho, on the discussion about that?
Someone was wanting an elaboration of why the velocity was 0 at the highest point.
Yeah, that's a good question. So the best way to see this is get a friend of yours to film you throwing an object in the air. I'm serious, because a lot of your phones have high-speed cameras on them. You can film at a high speed, and then you can do a slow-mo. And you will see that when you toss an object in the air, you will see it go up, up, and then for a moment, it'll seem like it freezes in place. The velocity at that instant is actually 0. And before that, the velocity was upward, and after that, it's going to be velocity downward. It'll come back down. That's why the velocity at the highest point is 0, because it literally is 0. And you can demonstrate this for yourself. Just toss something in the air. If you just toss it and you're just watching it, it might be too fast for you to visually see that with your own eyes. So that's why I'm saying film it. Get your phone, film an object going up and falling down. And you'll notice if you do a slow-mo, I think on the iPhone at least, where you can do a slow-mo and then you can see for a little elapsing of a certain amount of time, it'll look like it's just staying put at the highest point. So do that yourself and you can see. Other questions?
We have some questions about the acceleration and why we're able to pull it from the past instead of forward.
So for these questions, when you say there's an acceleration, notice that it has to be a constant acceleration to apply the 4 kinematic equations. And we haven't demonstrated this yet. We will later in the course. Why? That if you are only considering the effects of gravity, in the case of the hammer and the moon, the only thing that's actually affecting the hammer is gravity. If that's the case, regardless of the mass, how big the hammer is, it'll have the same acceleration for the hammer, the feather. We'll demonstrate that number is the same for all objects. And you need to deal with Newton's laws. And we're so far describing motion. We haven't talked about why things move. We'll talk about forces and accelerations when we talk about Newton's laws later in the class, and you'll see why that number is a constant number. For the moon, it's pretty clear because you don't have the atmosphere to deal with. On Earth, it's a little bit more complicated because you generally have air in your room. So when you drop an object, it is affected by not just gravity, but also air resistance. However, in most everyday cases, it's such a small effect that you can more or less approximate it as a constant acceleration due to just gravity. So 9.8 meters per second squared. Depending on the object you're on, there's a certain number that goes with it. It's a constant number. And for the moon, we calculated what that number was using the previous Instapol, and that's why we were able to use that number. You can also go to the moon and measure this. You can measure this to be the acceleration due to gravity, and then that way you have that number as well. So you can get that number in multiple ways. All right, so keep the questions coming. We want you to ask us questions. It's really important. So engage with us. We're happy to answer. The TAs and LAs will continue to answer your questions on that discussion as I talk too. So keep them coming. All right, what we want to do is now talk about a little bit of math before we get back to physics, because we need a little bit of math to get to projectile motion. So far, with one-dimensional motion, if you're dropping a hammer, for instance, with one-dimensional motion, you just need algebra and you're good to go. But when you're talking about two-dimensional motion, hitting a golf ball, hitting a tennis ball, trying to shoot a basketball, that's two-dimensional motion generally, and that requires a little bit more math to deal with. What do I mean by this? What I mean is that we need to talk about two different quantities that we'll encounter in this class. Scalar quantities versus vector quantities. So we're going to talk about scalars and vectors. When we talk about different terms in this class, they will fall either into one bin or the other. Scalars, by that what I mean, are things like speed. You're familiar with how fast you're traveling. You're walking, you're in a car, that's a scalar, 65 miles an hour, something like that. Distance, you might walk a mile, you might walk a kilometer, that's a scalar. Other things that are scalars, time, so if you read the time right now, 9:30 a.m., that's a scalar. And temperature is a scalar. Now, when you look at these, they look quite random. What does speed and temperature have anything to do with each other? And what's common with these things is that there is a number, let's say for the case of the temperature, it's probably, I don't know, going to be 95 degrees or so outside today. The common thing about a scalar is that it has a number and it has units that go with it. So 95 degrees Fahrenheit, 9:30 a.m., 2 seconds, 65 miles an hour. All these things are some number with units. So in math, it's slightly different. So if you've taken a math class and they talk about scalars, they will consider 2 to be a scalar in math. So in physics, it's a little bit more picky. When we say a scalar in physics, it's not just a number, but it's a number with units. So time is a scalar. The number 4 is a number 4. in physics. Right? So if you see that, just be aware of that. Now, when you're dealing with scalars, you can use arithmetic, the regular normal math you're familiar with. You can add, subtract, or divide. You can do normal arithmetic with scalars. That's the nice thing about them. Now, to contrast this, let's look at vectors. What are vectors? Velocity. So notice speed, velocity. In everyday life, maybe you switch these terms, no big deal. But in physics, velocity is a speed that has a direction. So 65 miles an hour is not a velocity. 65 miles an hour north is a velocity. So some speed with a direction is a velocity. So acceleration is a vector. So there are different quantities. We'll see force is a vector later on. There are lots of different vectors we'll encounter. And the common thing about this is that you have a number, you have units, and you have a direction. There are different components. The number, the units, that's common with a scalar, but key thing is there's a direction to vectors. And when it comes to vectors, you need to use vector math. If you try to do arithmetic, it doesn't work because there are different things. Just keep in mind we have scalars and vectors. We're going to talk about vectors. They're very useful, and you'll see in a second why that's useful, particularly when we're talking about motion in 2 dimensions. Let's say you start at the place you live, your apartment, your house, and then you want to go get some coffee at your favorite coffee shop. And then after that, maybe you go meet up with a friend. And each leg of this journey, let's say you travel that way from your place to the coffee place, 0.3 kilometers, and then you traveled to your friend, 0.4 kilometers. Now, if I asked you, how far are you from your starting point? After you get to your friend, how far are you from the starting point? This might seem maybe obvious, maybe not obvious. The point is it's a little bit vague of what I'm asking. Because in some ways you might say I'm 0.7 kilometers away from where I started. Because what I'm going to do is I'm going to do normal arithmetic, and I'm going to say I did travel 0.3 kilometers, I did travel 0.4 kilometers, therefore now I am 0.7 kilometers away. And in some ways this is correct in that it is the total distance that you have traveled. You've traveled 0.7 kilometers. However, it's not really how far you are from your house. Right? So if you were to take the shortest path from where your friend is to your house, then you're not necessarily going to travel 0.7 kilometers. Right? You might take instead this path. And by looking at this triangle, you can say that the length of this is not 0.7. And this is what we said earlier was displacement. Remember, displacement was a final position minus the initial position. Much easier to do in 1 dimension. If you're only moving in the x direction, then you might have 5 meters. The final position could be 7 meters, and you take the difference, and then that's your displacement. But now you have 2 dimensions to worry about. You have the x dimension, and then you have the y dimension. So this displacement is a difference between the final minus initial position, but we'll get into why you need to deal with this as a vector quantity. Right? So this is your displacement. So to answer this question, you can't do arithmetic. To answer this question, you have to do vector math. Let's talk about how you add and subtract vectors. Vector addition. Once you know how to add, you can subtract. We'll learn how to add, and then we'll see how this works. Let's talk about a couple of different ways to do this. One is you can do this graphically. What you're doing is you draw an arrow, a vector now. The term we're going to use is vector. You're going to draw a vector in the different legs of your trip. So I'm going to say vector R. I'm going to put an arrow. R is my displacement, how I traveled, the vector R1, my first leg of the trip, and then I'm going to put an R2 for the second leg of my trip. And when I want the displacement, when I want this direction, this distance here, what I need to do is just add the 2 together. So I just do this graphically in the sense I'm going to draw a triangle. I put the arrows next to each other, and I put the one arrow next to the other arrow, and I'm connecting from the starting point to the ending point. I make another arrow, and that is graphically the sum of these 2 vectors. Visually, that's fine, but most likely you're not going to do this graphically every single time because that's very tedious. It's good to see that that's how it's actually working when you add 2 vectors together. Graphically, that's how it comes together. But Let's make it a little bit more quantitative. The other way to do it is using a little bit of trigonometry. It seems a little bit similar to the graphical way of adding vectors. Again, we have the two vectors here, and what we're trying to do is trying to find this part of this triangle. And if you notice, this is a right triangle. We'll review from your math class, the Pythagorean theorem can be used. So if you have a right triangle, right, so here's your A, here's your B, there's two different sides, and if you want to find C, you know that it's A squared plus B squared is equal to C squared. You can apply this to your vector addition, knowing that one vector and the other vector are two sides of a right triangle. You can find the sum by using the Pythagorean theorem. If you were to find this, so this part, you can say that R1 plus R2, the magnitude of it, the two bars mean magnitude. The magnitude of this is equal to the square root of 0.3 kilometers squared plus 0.4 kilometers squared, the numbers of the two sides of the right triangle, and you take the square root to find C, and you can say 0.5 kilometers. That side of this triangle is 0.5 kilometers in length. When we say the magnitude is what's the length of this vector, and that's 0.5 kilometers. This is still a vector because we start here, we end here. This is still a vector, and a vector has to have a direction too, and we haven't really said what the direction is. We have only found what the magnitude is. But we can still do that using some trig. Let me redraw this. We have our right triangle, R1, R2, and the sum, R1 plus R2, is this. As long as we can identify this angle, that gives us a sense of a direction. We can say if this is north, it's so many degrees from north. How do we find that angle? We can use our SOHCAHTOA, so a mnemonic for remembering sines, cosines, and tangents. Given this angle, we want to figure out which of these do we want to use. Look at this angle. We know the opposite. We know the length of the opposite, we know the length of the adjacent, so we want to use our tangent, because tangent of theta is the magnitude of R2 divided by the magnitude of R1. So the opposite over the adjacent, which is 0.4 kilometers divided by 0.3 kilometers. And if you take the arctangent, you can solve that this angle is 53 degrees, and you can say from, say, north to identify the direction. Now, using some trigonometry, you're getting a little bit more sophisticated in terms of finding out what this vector is. Here's a vector, here's a vector. If you add them together, you get this other vector. We have now identified how do I find the magnitude of that vector? Use the Pythagorean theorem. Then once you use the Pythagorean theorem, you can use a little bit of SOHCAHTOA to figure out what this angle should be. So you have a direction, you have a magnitude, now you know what this vector is doing. So you know basically completely what this vector entails. The homework sometimes has this phrasing that I want to just make sure that I talk about. When you're talking about angles, sometimes they'll say stuff like north of east, and that confuses people. I think it's from probably navigation by boat or something. That's probably where these phrases come from. And what you want to do there is start off with of east. They might say 26 degrees north of east. What they mean is start with east. If you have your north, south, east, west, start east and then travel upward by 26 degrees. That's 26 degrees. You're going northward. When they say north of east, it means start of east, start with that part, and then rotate northward by that angle. And if you flip this, if you say east of north, that means start at north and then rotate eastward. That's the phrasing. You might see that in some of the problems. Just be aware of that. That's a bit of material here, so I want to make sure to answer any questions. So let's pause here, check with the LAs here. Are there questions so far? Good? Everybody okay? Don't hesitate. Please ask questions. If you've just forgotten a little bit of your trig, this is the time to ask. I'm happy to go over that, so don't hesitate.
Some confusion on the north of east.
Oh, yeah. So north of east. If you see a phrase like 26 degrees north of east, forget the first part. Just think of east as your reference point. You start in that east direction, and what they're meaning is go 26 degrees north in this direction. Let's try another one because I think that'll help. Let's say, Jericho, make up a number. 37 degrees, and let's say west of north. I'm just making this up. So west of north. If that's the case, what you're saying is, okay, of north, start north, and then rotate 37 degrees westward. And what you're talking about is this is your 37 degrees. If you had a diagram, it's a lot easier to show which way the angle goes. But if you have to use text to portray this angle, it's not as obvious as it seems. So you have to use some sort of phrasing to kind of say, okay, this 37 degrees, I don't mean this 37 degrees. So always better to start with the second part of this phrase. What is the of part? And that means that's your reference point. And rotate from that point in whatever direction, west, north, by the number that they're saying. Just be aware that phrasing shows up sometimes in problems, just so that you're not confused by it. Other questions? How do I get 53? Okay, once you have the tangent here, the tangent of the angle is this ratio. That's SOHCAHTOA. So a tangent of an angle is the opposite over the adjacent. That's the opposite side of the triangle. That's the adjacent side of the triangle. Put those numbers in. Once you have those numbers in, how you get the angle is that you take the inverse tangent, or arc tangent, same thing, of the two numbers, the ratio, 0.4, 0.3, and then if you plug that into your calculator, it will give you this angle. Try that out yourself. Make sure your calculator is doing what it's supposed to be doing, because another thing about trying this out while we have the lecture is that you're trying out your calculator, making sure things are working, you're checking my math. Don't just trust my math. I will make errors. You know, I'm a human. Make sure you're checking me, you're doing things yourself. Also, with angles, be aware your calculator can be in two settings, degrees and radians. Just be aware how to go back and forth. Sometimes the angle will be given in radians, so you'll have to use radians, and sometimes the angle will be given in degrees, so then you'll have to use degrees. Google your particular calculator to how to switch back and forth between radians and degrees. Make sure you're doing that, because if you're in radian mode and you do this, you're not going to get this number. You're going to get a different number. You're going to get 53 degrees only if your calculator here is set up for degrees. So check me, make sure you're doing that. Your calculator might show this as the inverse tangent or a tangent or arc tangent, same thing. If you need a little bit of brushing up on your trig, don't forget on Quest there is a set of modules for physics readiness, and one of them is on trigonometry. Go do a few problems just to remind yourself of how to deal with right triangles, how to do a little bit of Pythagorean theorem, do a little SOHCAHTOA. This is all going to help you later on, because this is going to show up over and over again, not just in projectile motion, but in Newton's laws, in momentum. It is to your benefit to spend a good amount of time making sure you know how to work with your right triangles. And come to drop-in hours, and if something's confusing, just please ask us. Is that okay so far? All right, so keep the questions coming. We have now looked at a couple of different ways to add vectors, and we want to now look at the most sophisticated, if you will, way of adding vectors. We're going to make our lives a little bit harder to make it easier. We're going to do a little bit more math, and then once you understand this, adding vectors is going to be very simple for you. It's going to take a little bit of getting used to, so we're going to make our life temporarily harder to eventually make things much, much easier. We want to now add vectors using unit vectors. Let's see what those are. Let's take our Cartesian coordinate system, x, y, z. You're probably familiar with it. Space that you're in, think of it as three components. Those are the three independent directions that you can move. So x could be positive and negative. I'm just showing the positive x part. Y could be positive and negative, and then z could be positive and negative. I'm just showing just the positive parts. So Cartesian coordinate system, if you can imagine the corner of your room to be the origin, and then you can have a x direction, a y direction, a z direction, and then anything in your room you can reference based on this coordinate system. You can say that your table is so many meters by so many meters by so many meters from this corner. You've likely seen the Cartesian coordinate system before. What you've not probably seen are the unit vectors that you can connect to each of these axes. Along each of these axes, we're going to draw vectors. I'm going to call them I hat for the one that goes along x, j hat for the one that goes along y, and then k hat for the one that goes along z. The reason why they're called unit vectors is because they are a length of 1. So if you're talking about position, it's say 1 meter. Each of these is 1 meter. If you're making a plot of velocity, for instance, then each of them will be 1 meter per second, for instance. So whatever you're plotting, these will take on a length of 1. They're always going to be the length of 1, thus the name unit vectors. They're always going to be stuck to the coordinate system. I hat's always stuck to X, J hat is always stuck to Y, and K hat is always stuck to Z. We'll see why are we dealing with this in the first place in a second. Let's go back to our coffee shop, going to meet your friend example. We started at a certain point, we traveled to a different point, and then we moved from that point to a different point. So there are vectors that you can use to depict how you move through space. And then when we wanted to figure out where did we end up? This vector, we did it graphically, we used a little trig. Now we're going to use a different way to do it. And what we're going to do is put our coordinate system at this place where we start off from. Generally, this coordinate system has 3 components, x, y, z, or I hat, j hat, k hat. But depending on how you're moving, maybe you only have to deal with 1 or 2, not all 3 at the same time. So if you look at yourself from a bird's eye view of you traveling around your city like this, it essentially looks like you're going in 2 dimensions. Austin's fairly flat. You're not really changing your elevation by a whole lot. Maybe you're not moving in the 3rd dimension very much. So it's more or less okay to just say you're moving in the y direction and the x direction. What we're going to do is take our starting point and put in our I hat and j hat. We're going to put in our unit vectors at the point where starting from. What we're going to do is write these vectors using these unit vectors. If I were to write R1, and we know that was 3 kilometers, that in itself is only a scalar. It doesn't tell me the direction, but I can use the I hat, j hat to tell the direction. I can say R1, the vector, is in the direction of j hat. We're going to outsource essentially keeping track of directions to the unit vectors. They're very good at keeping track of directions. So we're going to say, okay, unit vectors, go ahead and keep track of the directions because that's your job. So the job of the unit vectors is to keep track of directions. And we can say R1, the vector, it has a magnitude 0.3 kilometers, and its direction, we're going to just use that j hat. We know where j hat points, and we're going to say same direction as j hat. You'll see the R2, we know again the magnitude of that is 4 kilometers. And that's not a vector yet. And we have to say in what direction? Okay, it's the same direction as I hat. You can see that R2 and I hat point in the same direction. R2 has a longer length, of course. That's okay. That makes sense. R2, we can give it a magnitude and we can give it a direction based on what I hat's doing. So hopefully that's clear. What we're doing is writing the vectors in terms of the unit vectors, and that way we have references to which way these things are pointing. So far, I've made my life harder than it needs to be. You might be wondering, why don't I just use trigonometry? We were just perfectly fine doing that. So a moment ago, we can just use right triangles and do this. You'll see how powerful this is in a second. So if I say R1 plus R2, all I have to do is just add these together. The trick of adding them is to add i's with i's, j's with j's, k's with k's. You never mix and match them. All I'm going to do is when I say adding these two is I'm going to come here and say I'm going to pick out all the I hat stuff, add them together. There's only one. So I'm going to say 0.4 kilometers in the I hat direction. J's with the j's, but there's only one j. So then I'm going to say that's 0.3 kilometers in the j hat direction. And that is this result that we're after. If we're saying this is our vector that we're trying to solve for, this plus this is that, R1 plus R2, this is it. You're done because it has both a magnitude and it has a direction. Now, where is its magnitude? The magnitude's here because if you see, this is always going to be a right triangle. When you write it in terms of I, j's, and k's, because the fact that they're 90 degrees to each other, x and y, they're always 90 degrees to each other. Whenever you write something like this as I, j, k, each of them will be 90 degrees to each other, meaning that you can always use the Pythagorean theorem on this. If you wanted the magnitude of this vector, take this squared plus this squared and take the square root, just like we did before, you're going to get 0.5. So the magnitude of this vector is already here, and also the directions are already property here. It's saying that the sum, it has components in the I hat direction and the j hat direction. A little bit of it is in the I hat direction, a little bit of it is in the j hat direction. It's a bit of both, which you can visually see, yes, that's true, because that is going a little bit in the I hat direction and a little bit in the j hat direction. Okay, so far, same thing as trigonometry. You wouldn't see any benefit, so why would you do this? Now, why is that, okay, let's just say that this is now, we're going to call this R3. Our result we're going to call R3. And if I say, what if there's another vector that I give you, R4, 0.4 kilometers I hat plus 0.2 kilometers j hat, I give you another vector, and I say, okay, I want you to find R3 plus R4. Now, in the trig way of doing things, you'll have to draw another picture. You have to do the Pythagorean theorem again, and then go through and find SOHCAHTOA and find the angle. This is much longer, you'll see. The more times you have to add vectors, the more tedious it's going to become. In the case of unit vectors, all you have to do is just add apples to apples, oranges to oranges. So if you're adding R3 to R4, all you have to do is add the I components together. So you gather them and add them. That'll become 0.8 kilometers in the I hat direction. And then you add all the j's together. So then when you do that, you get 0.5 kilometers in the j hat direction. And then that's your result, and you're done with that. So it's very powerful because it gives you a very fast way of adding, subtracting. You can subtract vectors using this method as well. As long as you're keeping i's with i's, j's with j's, you're never mixing and matching. You're not adding this number to this number. As long as you're adding just the i's together, just the j's together, then you can quickly do vector addition. All right, questions about unit vectors. This is probably unfamiliar to most of you, so this is likely very new stuff, so take a moment, ask us questions. Anything that's come up so far? Okay, so let's do another Insta poll here. Take a look at this prompt, make sure you're drawing a picture. Be very helpful for you. Let's try to work this out. What we're looking for is the displacement at the end of all this traveling. Ask questions on that discussion, and we'll be back in about a minute and a half. So hopefully you're working on it and asking us questions. Questions about this? How are we doing in terms of, okay, we got the first response, 3 plus 4, j hat. Popular answer. I'll draw the x and y. This is my coordinate system. Let's start in the middle. Let's start and say how we're traveling. Travel 3 kilometers west. Now this is where you'll have to map two coordinates together, where you have to put x and y and the directions, the cardinal directions, west and north down in the same sense. I think the easiest thing to do is imagine bird's eye view, x and y in this orientation, and north is upward. When you say 3 kilometers west, starting from here, you might say you go that way. That's west by 3 kilometers. And it's in the negative I hat direction. Positive I hat goes along the x direction, positive x. 3 kilometers in the negative I hat direction. Then you travel 4 kilometers north from that point. 4 kilometers positive j hat. And then after that, you're going east. So you're going east, 6 kilometers, positive I hat. Then where do you end up? You started right here, you ended up right there. The vector that represents where you started and ended is this. This is your vector. And what you want to do is add everything up. You want to add all your vectors together to get your resultant displacement. How do we do that? We add up all the i's with the i's. I's, we have a negative number and a positive number here. You add those together, you're going to get positive 3 kilometers in the I hat direction. You add all the j's together, there's only one j, positive, so we'll say that's positive 4 kilometers in the j hat direction. This vector is represented by this. So 3 I hat, 4 kilometers j hat. Hopefully most of you are seeing fairly straightforward once you get the hang of the i's, j's, and k's, the unit vectors. Adding vectors becomes fairly straightforward as long as you remember i's goes with i's, j's goes with j's. And then if there is a third component, the k's will go with their k's. Use the simulation that I showed earlier to visualize how something would move in 2 dimensions as we work through projectile motion problems. If I reset here, Let's try to reset and shoot this cannon off, and you can see how the object moves through. You can think of it like a basketball if you're shooting basketballs. That works too. And another way to do it is also through a demo. So we're going to look at this demo video that's going to show something cool about projectile motion, and we'll come and talk about it some more. In this demo, we're going to look at what happens when there are two objects that fall in two different ways. One will fall directly down, and this object will fall with some velocity in this direction. And that horizontal direction will have some velocity, and we'll see the difference in how these objects fall. If you take a minute to think about what may happen, two objects falling, this one has a little bit more velocity, maybe you'll think that they will fall at different rates, or you might think that they fall at the same time. We want to see what happens. Let's load this up. So this is a spring that I'm going to load. So when I release this, this object's going to get shot off in that direction and will still fall, but then this object is going to fall directly down. They're equivalent masses, so we'll see what happens. I'm going to release this, and let's see which one comes down first. As you'll notice, they would have come down at the same time. They fall at the same rate. And that's because two different motions, so if motion in the x direction or the horizontal direction and motion in the y direction, they're independent. Even though this object has an extra velocity in this direction, it still falls. Gravity still works on this, just like this other object. The time it takes for them to fall will be exactly the same because gravity is working on both of them. Let's go to our notes here and draw a picture of projectile motion. Let's say some object moves like this. Let's say you throw a ball in the air, you're playing catch with your friend or something like that. So you're throwing the ball, it will go up and it'll come back down. This is the path you're going to see for a projectile motion. You could be up at a building, maybe shoot off something sideways and it'll do this. So depending on where you're starting and ending, it might have different specific shapes, but generally speaking, it follows this sort of path. So the ball might do this. Now, when you're doing this, think about the velocity of the ball. Think of it a vector. If you think about at this point, you can draw a vector that shows you the velocity of the ball there. And just before it comes down, maybe the velocity of the ball is like this. Your vector is pointing that way. And everywhere along the path, you can draw the velocity vector. Here's the vector, velocity with the arrow, velocity vector. And when it's at the top, you'll notice that it goes sideways. The velocity vector is sideways, and then here it's pointing this way. You get the idea. Everywhere along the path, you can almost freeze the film and say, okay, what is this velocity vector doing? And notice that the velocity vector is changing. That's one thing to notice. You can use your trig now. So if I say I'm going to zoom into this velocity vector, which kind of looks like this, I'm going to draw it on the side, and say that is the velocity at that moment of the object, the ball, let's say. And knowing your xy coordinate systems, knowing the unit vectors now, you can break this vector down into its component parts, because this vector is made up of an x component and a y component. There's a vx and a vy. This is where your trig comes into play. We looked at how calculus is useful when we're talking about kinematics. Now we're talking about projectile motion. Now you're seeing where trigonometry is very useful. This vector, anywhere along the path, has this blue arrow, the vector, but at any point you can break this out into x and y components. They're not always going to be the same. As the velocity changes, these components will change too. We'll have to think about that. Here's our velocity. We can always break it up into component parts, and if you want to write the vector, you can say the vector velocity is made up of the x component of velocity in the I hat direction plus the y component velocity in the j hat direction. That's the vector form, which we talked about earlier about unit vectors. This is the power of unit vectors coming in, where you can see, okay, the x part gets added to the y part, and that makes up this part. This is how you get the vector. Okay, the key idea here, when you're doing projectile motion questions, mentioned in the demo, the key idea to remember is you want to treat motion in each dimension independently. You want to focus on x and do stuff in x, and then do stuff in y, and then we can do some algebra at the end afterwards. But you always want to think x is doing its own thing, y is doing its own thing, generally speaking. Now, this might not be the most obvious thing, because when you watch something go up like this, you know it's going through x and y at the same time, so you might say, well, they're kind of connected, and they are in some ways. But when you're actually working out the equations, you want to think of it as separate things, and we'll get into the deep underlying reason for this. It's not just comes out of nowhere. It comes out because of a specific reason due to Newton's laws. So we'll get into the why later of why this actually works this way. But you want to treat the motion in each direction independently of each other. When we are looking at projectile motion, we're always considering cases where there is an acceleration downward, usually due to gravity. We're considering acceleration due to gravity is downward. So whether you're on Earth, you're on the moon, and that's the only external effect we're going to consider. We're not going to consider air resistance, because then that would be an acceleration in the horizontal direction. That's a complication. We'll get to that later. When we're starting off, all we need is an acceleration in the y direction. That's what we're going to just consider, just the constant acceleration due to gravity. Now, this is acting in the y direction, negative to be specific, negative y direction. This has zero effect on x. That's important. The velocity in the x direction does not care about the acceleration in the y direction. It's not its problem. Because the acceleration is only in the y direction, it only affects the velocity in the y direction. It does not affect the velocity in the x direction. That's where this is coming into play. Okay, we'll see more of that as we go through. Be careful and make sure you're aware of the independence, x and y. Okay, so for projectile motion problems, you're usually given an acceleration due to gravity, usually the Earth. Sometimes, because it's me, we're going to throw some moon examples. But mostly it's going to be for the Earth, acceleration due to gravity in the y direction. Assuming that positive is upward, we're going to say it's negative 9.8 meters per second squared. A number you can measure doing experiments, a number we're going to see theoretically why this has to be the number later on once we talk about gravity. In the x direction, we're going to say that the acceleration is 0 meters per second squared. We're ignoring, for now, for simplicity, air resistance, so there's nothing accelerating in the x direction. Based on the definition of acceleration, we should know that when we say that the acceleration is 0 in a certain direction, what we also mean by that is that the velocity in that direction is constant. Because if it's not accelerating, the velocity is not changing. So the x component of the velocity will be constant. Those are usually where you're starting from. So that's for a projectile motion problem, that's your starting point, the accelerations. Now, let's come up with some equations. We want to model our motion through two dimensions, and we'll start one at a time. We'll talk about the horizontal motion, the x direction first. Come up with some equations to describe the horizontal motion. This is the actual path of the object, but we want some equations that just talk about the x direction only. What can we say about the x direction? We can say something about the velocity. We can say that the velocity at any point in time is equal to its initial velocity in the x direction. It has to be. It doesn't accelerate in that direction. In terms of position, we can say the position at some point in time is the initial position in x plus the velocity of x times time. They're the same. So the initial velocity times time will tell you how far in the x direction something will be going. So it reminds you about the kinematics. You're still using the kinematic equations, but unlike the case of one-dimensional motion where you took those four kinematic equations and applied it, in the case of projectile motion, when you have two dimensions, you can use all those kinematic equations twice. You can have those equations describe the x motion or the horizontal motion, and you can use those same equations to describe the y motion. Because in both cases, it's constant acceleration. In this case, it's constant is 0. In the y case, it is a negative approximately 10 meters per second squared. We have the equations to describe horizontal motion. Let's now consider the vertical motion, or y direction. We need some equations to describe the y. In the y direction, there is acceleration. We want some equations that actually consider that acceleration. Let's come up with a position equation. So we have one from kinematics that we can use. This we've seen before. Now applying it just to the y direction. Position in the y at some point in time is its initial position in y, velocity in the y direction initially times time plus 1/2 at squared. You may see this in a slightly different way. These are equivalent. This is to saying that if you take this equation, you can write it in a slightly different way too, which you will see as well. Sometimes we might say negative 1/2 gt squared. In this case, if you see this form of the equation, the g is a magnitude. So 9.8 meters per second squared. The negative is already accounted for. Don't also throw a negative in here. In this case, this is a more general form. So if you're going to put 9.8 meters per second squared, you probably want to put a negative in here. Just be aware, you can write this in different ways. If you're not sure, you put a negative when you shouldn't have, you will do the work and it'll give you something nonsensical, like you drop something and it fell upward or something. The nice thing about kinematics, you'll be aware that something's not correct. That's the nice thing. You don't have to get surprised by it. If you do something and you didn't account for the negative correctly, it will tell you. It'll become very apparent that you drop something and it has a velocity upward or something that doesn't fit. Okay, we have a way to describe the position in the y direction. Let's come up with a way to describe the velocity. So we can say velocity in the y direction squared at some point in time is the initial value squared plus 2 times the acceleration, final y minus the initial y. Another kinematic equation we can write, and just like before, we can also write it slightly differently if you see it with a negative sign. If you see it with a negative sign, remember the g is a magnitude there. So don't put another negative sign because then it's not going to work. I think these are the better ones to remember because they're more general. In the equation sheet for the exam, for instance, I'm going to list these with the A because then it leaves it open to what A is. This makes it specific to free fall. That is a acceleration due to gravity, and it's already accounting for the negative, so I feel sometimes that confuses people. Let's think about going back to hitting golf balls on the moon. Let's ask a question about how high would the golf ball go up? It's a practical question. Playing golf, you're hitting the ball, and if you were to show a diagram of what that would have looked like, the ball probably looked something like that, traveling on the moon. And we want to know, okay, how high did the golf ball go? What was happening right there is our point. Because we want to know what that height was of the ball. We don't know. It's something we wanted to figure out. With this, you want to come and think about, okay, what's going on at this point? As the ball travels, there's something that happens to the velocity at this point, which we talked about earlier in the class. It's not that the velocity here is 0, like the previous case. If you threw the hammer up, at the very highest point, the velocity of the hammer will be 0. But in the case of a projectile, if you're hitting a golf ball, that is not true. At this point, it's still moving. But the movement is completely sideways. It's only in the x direction. It's at this highest point, it's only moving in the x direction. What is true is that the velocity in the y direction is 0 at, let's say, h max. Here's the maximum height that the ball will get to at h max. This is true. Velocity in the y direction is 0. That means you can use our kinematic equations. We can say velocity in the y squared is equal to the velocity initial in the y squared minus, we can say, let's use this one just for some practice with the negative sign one. Okay, we're using our kinematic equation, y final 0, y, the velocity in the y final is 0, y, the height, this is just the maximum height. We're starting off at I of 0 here, and now we can solve for this. We can say max is equal to the initial velocity in the y squared divided by 2 times g. You can see, using kinematics, you can now figure out, as long as you knew how hard he hit the ball, you know the acceleration due to gravity on the moon, you can figure out, okay, that's the maximum height the ball would get to. We're putting kinematics together in 2 directions now. It's getting a little bit more complicated, but it also allows you to solve more complex problems, not just in 1 dimension, but in 2. And once you know how to do that, you can extend it to 3 dimensions if you like. All right, so let's stop here. We'll pick it up tomorrow. Make sure you're starting on your homework if you haven't done that already. Come to drop-in hours. We're available today. Click on those Zoom links. So we're happy to help, chat about anything so far. So we'll see you tomorrow.